Hi, this is section 1.3 in AP Calculus, and this is dealing with limits, and we're going to try to evaluate limits and do this analytically. Excuse me. And so if I get some problems, I could look at it graphically and with tables like we did before, but I think we found quite a few patterns when we were doing this. And the patterns turn out to be that if I have some sort of continuous function, and we haven't talked about continuous too much, but I think you can get an intuitive idea about that. But if I have some continuous function, if I plug in this 3 into here, that will give me the y value that I'm approaching, and that's pretty much what we're going to be doing. We will run into some situations where we get a 0 in denominators and some other things, but we'll try to resolve those. So to find the limit of this first one, I'm going to start by just taking the 3 and I'm going to plug it in to this function. So if I square 3, that's 9 times 3, 27. So I'm going to get 29. And so that's just direct substitution. Evaluate a limit by direct substitution. It works. No problem. Try this next one. If I plug in 1 plus 2 plus 5, I'm going to get an 8. And then on the bottom, I'm going to get 2. So this limit would be overall 4. Why don't you try the rest of these by direct substitution and see what they yield, and then I'll put up the results. So I've done a few of them here, and you can double check your work on those. These, you got to remember your trig functions, and this is where it's kind of nice. We don't review the trig functions, but we plug you right into these, so you got to remember what these values are. So if I do the secant of 0, that would be 1 over the cosine of 0. Secant is 1 over the reciprocal function of the cosine. So cosine of 0 is 1, so this is going to be 1 over 1. Turns out to be 1. 0 here, what's 0 times 1? Well, that's going to be 0. And if I plug in 0 into the next one, that's going to be 1, and then we have to square it. This squared means that it's the whole cosine of x value, and then it's squared. So that would just be 1. And then the limit of the secant here, secant, that would be 1 over 0. Can we do 1 over a 0? No, we're going to have a vertical asymptote. So this one does not exist. Does not exist. Okay? Here are the rules that you can also find from your book. But really with these, if I have a y value here, which is b, any limit as x goes to some x value, I'm going to get out that y value. So the limit of x going to c of b is going to always be b. For this one, this is where we start using the direct substitution. So if I take c and I plug it in there, I'm just going to get out c, direct substitution. This one, if you have an exponential function, I'm sorry, this is a polynomial. Take the c and plug it in there, you're going to get a c going to n. C to n. My language is funny today, sorry. So this is just a direct substitution. So all of these that I'm going to show you just come from direct substitution. So this next one, scalar multiple. That just means that if I have b times some function, and then this limit of as x approaches c of f of x is equal to L, I'm just going to take that scalar, which is the b, and multiply by L. And this is really direct substitution. It's the same thing. This one's direct substitution too. If I have the sum of two polynomials or two functions, I can take c and plug it in and I get the two limits out. Product, same. Quotient, same, provided k does not equal 0. And then if we have something raised to a power, we're going to get the limit raised to the power. And you can go through all these and they're pretty much the same. If I have a rational function, I plug in c, making sure the denominator is not equal to 0. Direct substitution on this one. Direct substitution, this is a composition of functions, but it's a direct substitution on a composition of functions. Here, if we have our trig values, same thing, just direct substitution, plug it in. I think you're getting the idea. Okay. That's a different topic. Okay, if we go back to our note sheet, we have two techniques that will help us resolve a 0 over 0 situation. So if we do a direct substitution and it yields a 0 over 0, that is what we call an indeterminate form. And with that indeterminate form, somehow we have to resolve that 0 over 0. One way is through cancellation, which might give us a hole in the graph that we've looked at in pre-calculus. And then also the other method would be the rationalization technique, which will use complex conjugates, not complex, but conjugates. So if I look at this one, first of all, I plug in 1. I'm sorry, negative 1. If I plug in negative 1, I'm going to get 0 over 0. So this is my indeterminate form. So when I see this indeterminate form, I'm going to have to try to resolve it if possible. So I'm going to take and I'm going to factor this one. I have x plus 1 in the denominator, and in the numerator I can factor out x plus 1 as well, so this would be x plus 2. So if I factor and cancel, this will behave just like the function x plus 2. This function here is the same as x plus 2 everywhere except for at x equal to negative 1. I do have to write this limit in all the time because I have not evaluated a limit yet. Now that I do direct substitution, I can take out, and I don't need this limit notation anymore. So I go negative 1, plug it in, and I'm going to get 1. And with this, there is a hole in the graph. That's a situation that we looked at in pre-calculus. We also have something that's called the rationalization technique. This is for when we have radicals. And we want to try to get rid of some of these radicals so we can evaluate it. Well, first of all, let's make sure we get 0 over 0. If I plug in this 0 through direct substitution, I get 1 minus 1. Yep, that's 0 over 0. So what we do instead then is we go ahead and multiply by the conjugate. If you remember what the conjugates are, conjugates are just, if I have a plus b, the conjugate would be a minus b. And so in this situation, this is my a, this is my b. So I'm going to multiply top and bottom by the conjugate. And I can multiply by 1, that's no problem. And when I do this, remember that this becomes a squared minus b squared. So the middle terms drop out. That's the whole idea, so we get the square root to drop out. So this would be, don't forget the limit, this would be x plus 1, which is my a squared, and then this is my b squared, so I'm going to get minus 1 all over x times this big thing. Now I can try to plug in, well, let's see, it still doesn't work. Limit, x approaches 0. The idea here is that I could cancel the x's now. So I'm left with this. Now I can do a direct substitution, so I end up with 1/2. So really, it's multiplying by the conjugate to get rid of the square root, and then a lot of times what happens is that you can end up canceling. So here you cancel out, and that gets rid of the 0 over 0 situation. Then you just plug in 0, and then you get 1/2. So this box summarizes finding limits. And so what you'll try to do is, first of all, you try to do direct substitution. That's always the easiest way. If you get 0 over 0, though, then you try to find a function that agrees with f at all the points. Well, that's pretty much factoring and canceling, or else the rationalization technique. And then, since they agree in all the places, f and g agree everywhere except for in one place, that still means that the limits would be the same, so that would be your g of c. Then use a graph or table to reinforce your conclusions. Now I'm going to give you 2 more special trig limits, and I want you to do these on your calculator and zoom in and see if you can figure out what the limits would be. But the first limit deals with the sine, and the second limit deals with the cosine. So we're going to take the limit as x approaches 0 of the sine of x over x, and figure out what that might equal. And then the other one is the limit as x approaches 0 of 1 minus the cosine of x over x, which can equal a few different things too. So go pause this and go do that on your calculator and see if you can figure out what the limits are. So here's the graph of sine of x over x. If you look in there, it looks like as x goes to 0, we go to 1. But if you go to the table, you'll see that if I plug in a value of 0, it is undefined there. So there is a hole in the graph, even though it doesn't necessarily appear to be like that, which makes sense because we're dividing by 0. Now back to the notes. So this one is equal to 1. And if you did this one, hopefully you found out that this one would be 0. Okay, so you can check those out. Similar ones to this, since it does go to 0, I can do a lot of manipulations. This one is equal to 0. And this one just turns out to be factoring out a -1. -1 times 0 is still 0. And then there's a few other repetitions of that one that you can find too. So if you graph those, and that's what happens. You can prove this one with the squeeze theorem, and they show it in the book. I think the best way to see it is with the calculator, though, is if I graph both sine of x and x, if I graph this and you zoom in and you look very, very close to 0. So when we zoom in here, both of these curves looks almost identical, and when they get closer and closer to 0, we could keep on zooming. They will look identical, and when you take anything divided by itself, you're going to get 1, and that's what's happening. Although we are dividing by 0, it's going to look like, well, it's going to be undefined at that specific point. Now let's go to some examples, and let's see if we can use our new limit formulas to deal with these. If I look at this one looks kind of like what we can deal with the limit as x goes to 0 of the sine of x over x. And so, and not exactly, but we can make it happen. X goes to 0 of 1 minus cosine of x all over x is equal to 0. If I maybe factor out the sine of x here, so the limit is x goes to 0, I factor that out, I get 1 minus cosine of x all over x squared, so I can put an x here and an x here. So I just split up that x squared. This right here would be one of the limits that we're talking about. This would be the other limit. So this is really 1 times 0, which is equal to 0. Going on to the next one, this one, in order for this rule to work, instead of having x here, maybe I would have u. I could have a u which would represent any function of x. So here I need the 5x down here. To put a 5x in, I can just write a 5, but that mathematically is incorrect. But I also can balance it off by putting a 5 there. So really I've just multiplied by 5 over 5, which is just 1. So now this part right here, as x goes to 0, both of these will go to 0 at the same pace. So this overall limit in here is simply 1, and then I have my 5, so I get 5. So it's 5 times 1. This one's similar, but I don't have this. I just need a plain x. I have the additional 5 here, but through simple multiplication I can pull that out. So the limit as x goes to 0 of 1/5 sine of x over x is equal to, well, that's 1/5 times 1. So there's an example of doing some algebraic manipulation. Now we're going to go to the definition of the velocity function. This right here is instantaneous velocity. That's the velocity definition. It's the limit as t goes to a of s of a minus s of t all over a minus t. A is a constant, and then t you keep as a variable. And so under this situation, we drop a ball from 800 feet and it's modeled by this right here. What we want to do is find how fast the ball is falling at a equal to 3. So that's my constant. So my velocity at time 3 is going to be the limit as t approaches 3 of s of 3. I'll write this all out. And now we just replace the it into this function. We keep writing this limit until we actually evaluate it. So I put this 3 in there, negative 16 times 9. Let's just keep it like that. Minus, plus 800 minus, now I got to do s of t. Keep the t in there. We don't plug anything in for that yet. And we get negative 16t squared plus 800. All over 3 minus t. Now, why I could do a direct substitution right now if I take this 3 and plug it in here, but I'm going to get 0 over 0. So that I need to resolve. So somehow I need to simplify this, factor and cancel. So I go the limit as t approaches 3. If you look here, this 800 will cancel with this 800 because I have a minus sign here. And then here's a negative 16 that's in common. I'm going to factor that out. And so I get a 9, and then the negative 16 I took out, so I still have a negative, so it's minus t squared all over 3 minus t. Now hopefully you can see what's happening here. Limit as t goes to 3 of negative 16, this would be 3 minus t, 3 plus t all over 3 minus t. This and this will cancel. And now I can do a direct substitution. If I do a direct substitution, I don't get 0 over 0 anymore. I take the 3 and plug it in there. Negative 16 times 6 would be negative 96. Now we should also determine the units. For you people in physics, you can figure this out probably pretty quickly, but what we're doing is we're taking the position and dividing by the time. Well, the position is measured in feet, and the time, I don't know if I have it set on here, but it should be seconds. So this would just be feet per second. That's my velocity. Now, at what time does the ball hit the ground for part B? That would just be an algebraic thing. So that would be your height would be 0. So I'm just going to go 0 is equal to negative 16t squared plus 800. Now you should solve for t here, and you should get only the positive value because we're not looking at negative values. And what you do with that positive value is that you plug it in here and you do exactly what we just did, except for you use the different value. So try this with that new value. So check to see if you can do this. We'll check it in class 2, so please make sure you go through that. Now finishing up, how do you evaluate these things? Well, what you do is you do direct substitution. This is evaluating a limit. Direct substitution, plug it in. If you get a specific value, then you're done. If you get 0 over 0, you have to use the rationalization technique or the cancellation technique or the special trig limits to evaluate. If it's undefined, division by 0, which is not this case, then the limit just doesn't exist. This is 1.3. Thank you very much, and we'll do this work in class.